Hello, my name is Bowden Hu. Today, I'm presenting a research done at UT Austin on modernizing GPGPU benchmarks. Today, the computing power of GPGPUs are growing rapidly. Every new release is able to perform more flops than previous generations. We also observe a trend of growing size of on-device memory. For example, the newest NVIDIA 800 has 40 gigabytes of memory, which is a big leap from previous generations. These changes often come with adjustments in architectural design. In addition, these devices are offering more and more programmability, making them resembling general-purpose multi-core CPUs. For example, early GPUs requires reformulating computational problems in terms of graphics primitives, which is a cumbersome process. Frameworks such as CUDA allows programmers to ignore the underlying graphical concepts and focus on computing concepts with general-purpose programming languages. On the other hand, modern GPUs offer better system integrations. Features such as unified memory blur the lines between host and device even further. Here's a list of new or recent hardware features introduced in recent NVIDIA GPUs. Hyperqueue increases the total number of work queues between the host and the device by allowing multiple simultaneous hardware-managed connections. Tensor Core is a specialized programmable matrix multiplied and accumulate unit that is specifically designed for training and inference applications. Naturally, they would dramatically increase floating point compute throughput. RT Core, independent of traditional CUDA cores, is another specialized unit designed for ray tracing applications. The MIG also stands for multi-instance GPU, introduced in A100, allows a single GPU to be partitioned into separate instances and provide multiple users with separate GPU resources. Each instance has separated and isolated paths through the entire memory system. And here is a list of new software features introduced in the CUDA ecosystem in recent years. Unified memory address creates a pool of managed memory shared between the CPU and the GPU. This memory region is accessible to both CPU and the GPU with a single pointer, and the data transfer could happen through the demand page mechanism. This is different from the traditional approach where the CPU and the GPU memory must be initialized separately, and the data transfer is managed completely manually. Cooperative groups provide the ability for programmers to define and synchronize groups of threads smaller or greater than thread blocks. This feature provides additional synchronization flexibility than traditional synchronization construct, which only work on thread block basis. This feature could potentially provide greater performance and design flexibility. Dynamic parallelism is a feature supported via an extension to the CUDA programming that enables a CUDA kernel to create and synchronize new nested work, which is different to the traditional approach where CUDA kernel launch is only invoked on the host side. The last feature is CUDA graph, which allows work to be defined as graphs rather than single operations. It visualizes the work dependencies and provides rooms for faster kernel launch. Since these new features will likely have direct impact on application behaviors and performances, it is important for applications to be updated with them. However, existing benchmarks such as Rodinia, Shock, Mafia, and Parboil have not been updated with some of these new features. Aside from new hardware and software features, we also notice that input data sizes have direct impact on application behaviors and performances. Take k-means, for example. The utilization level of the streaming multiprocessor and the memory system seems to be very well balanced, with input data sizes roughly around 10 megabytes. However, as we increase the number of points, the pressure starts to shift away from the streaming multiprocessor onto the memory system. So what appeared to be a well-balanced application turns out to be memory-bound application simply because the input data size changes. Finally, it is also important for benchmarks to keep up with emerging application domains such as deep neural network and ray tracing. This has led to the creation of the Altis benchmark suite. Altis benchmark suite focuses on varying data input sizes so that applications can be tested under different workloads. Every application has 4 preset data sizes, with some application also taking user input, adding the extra variation of input size. Altis also exercises new CUDA features. These CUDA features include unified memory, hyperqueue, dynamic parallelism, cooperative groups, and CUDA graph. The Altis benchmark suite has 3 levels of benchmarks, resembling the Shock benchmark, also the scalable heterogeneous computing benchmark suite. Level 0 include benchmarks that stresses low-level device characteristics. Level 1 include benchmarks that are essentially low-level primitives, such as matrix multiplication and BFS. Level 2 include benchmarks that represent application-level workloads, such as clustering and k-means. Currently, the Altis benchmark suite only supports CUDA because AMD has lagged behind in terms of supporting these new features. Here's an overview of Level 0 benchmarks. The benchmarks in this level focus on low-level device characteristics, such as bus data transfer rate, bandwidth of different components of the memory hierarchy, and the floating point operation capability of the device. These benchmarks are adopted from the SHOC benchmark suite. The Level 1 benchmarks include low-level primitive applications. The GUPS benchmark, also stands for giga updates per second, is used to test the capability of random memory access. The breadth first search is a commonly used graph traversal algorithm. The general matrix multiply benchmark is used to measure matrix multiply performances of the device, which is usually computationally bound. The Pathfinder performs shortest path algorithm to focus on stressing irregular parallelism, as different CUDA threads could take different paths during execution. The sort benchmark performs fast radix sort on integers. Both BFS and Pathfinder are adopted from the Rodinia benchmark. The general matrix multiply and the sort benchmarks are adopted from the SHOP benchmark. The GUPS benchmark is adopted from the HPCC benchmark suite. Here is an overview of the Level 2 benchmarks. This level covers a wide range of application domains such as fluid dynamics, video compression, and computer vision. These applications come from a variety of sources, including Rodinia and SHOC. To find more information about these benchmarks, please refer to our paper for more details. Here we're going to discuss about k-means, which is an old benchmark but provides Altis with many opportunities to exercise new features. Here is a sketch of how it works. K-means have several stages of execution. First, the number of centroids is defined and then randomly initialized. Next, we compute the sum of the square distances between the data points and all the centroids. Then, each point is assigned to the closest centroid. Finally, the average of the data points are taken as the new centroids. This process is repeated for several iterations until the centroids converge. This is a picture of the Tesla P100 memory hierarchy. Normally, during the mapping center stage, the centroids will be put into the constant cache for fast access time while all the other data is put into the global memory. During the accumulation and updating stage, all the other required data will be shifted into the host memory. Here is a simplified view of the data management during k-means in the Rodinia implementation. Calculating the distances between data points and centroids is done on the GPU side. Each CUDA thread is mapped to exactly one data point. All data lies on the GPU memory in this stage. Then, the membership information is moved to the host memory to calculate the new centroids, which is then moved back to the device memory. This data movement is performed manually and happens during each k-means iteration. In Altis, we incorporated unified memory to automate this data transfer process. Here is a graph showing the performance between manual data transfer and demand paging. We can see the application performance is not affected that much when the data size is small. It only starts to slow down when the data size increases. There are several factors here. First, the size of membership information is directly proportional to the number of data points. Therefore, the more data points there is, the more demand paging happens. Second, the paging also occurs before the beginning and after the k-means trending, as all data points have to be read into the device memory first. Third, because accumulation happens on the CPU, which performs accumulation in a serialized region. The more points we have, the more operations are required for accumulation. It's worth mentioning the number of centroids are usually not too large to avoid creating artificial boundaries within real data set. Therefore, the demand paging cost for moving centroids information is relatively low. Here we can see that the original k-means implementation in Rodinia introduces overheads because of the constant data movement and the serialized execution on the CPU. To further speed up the application, we moved the accumulation stage and the centroids updating stage onto the GPU in Altis. This eliminates the constant data movement between the host and the device. Furthermore, we can perform parallel accumulation on GPU for more speed up. In Altis, we provide different implementations for accumulation and centroids updating to test how application would respond to them accordingly. Now we've eliminated the involvement of CPU operations during k-means. Can we add any more optimizations? Now we've moved from the GPU plus CPU implementation in Rodinia to purely GPU implementation in Altis. We notice that the GPU is launching 4 CUDA kernels, each representing different stages of the k-means during each iteration. The presence of these kernels is required by the current CUDA programming model to ensure thread blocks operating in one pipeline stage has produced data before thread blocks in the next pipeline stage can consume it. With cooperative groups, we can provide global inter-thread block synchronization, which allows us to reconstruct a kernel with persistent thread blocks. What that means is we can combine these 4 separate kernels into a single kernel by using grid synchronization provided by cooperative group. This kernel can be launched through the CUDA Launch Cooperative Kernel API. Here is the result showing the speedup when Altis uses the cooperative group implementation. The test is conducted with 16 centers, each having 16 features for 30 iterations. We can see there is a consistent speedup and the number of points is relatively small. This is because the traditional all-GPU implementation in Altis has kernel boundaries between each kernel launch. These kernel boundaries carry an implicit invalidation of state, and with it, potential performance implications. Removing them enables speedup in our application. As soon as we pass a certain threshold, however, it seems the speedup suddenly stops. This is because, to guarantee co-residency of the thread blocks on GPU, the max number of blocks launched will be limited. To find out the exact number of launchable blocks, we pass the kernel to the CUDA occupancy max active blocks per multiprocessor API. The result is multiplied by our intended thread block size and the number of streaming multiprocessors on our device, which yields 40,960. This means we are only able to launch that many of CUDA threads. The traditional implementation in both Altis and Rodinia has a one-to-one mapping between data points and the CUDA threads. However, the number of threads being limited using grid synchronization, we have to map each thread to multiple data points. Therefore, the more data points we have, the more processing each thread has to do, resulting in slowdown. We also engage in similar optimization efforts with other workloads in Altis. The next application we're going to look at is the GUPS, also stands for giga updates per second. This benchmark is a measurement of computer performance. GUPS is a measurement of how frequently a computer can issue updates to randomly generated RAM locations. It stresses the latency and especially bandwidth capabilities of a machine. The formal definition of this benchmark is as follows. First, we let T be a table of size of 2 raised to the power of n bytes. And here we can imagine T as the system memory. Then we let A be a stream of 64-bit integer of length of 2 raised to the power of n plus 2, generated by primitive polynomial over the Gauss field. And then, for each entry in the stream, we will use the highest n bits of each entry to randomly locate a location in the memory, which is also the table T. And then we will update the value in that location by performing an XOR operation with the value A. Now, usually the number n is defined as the largest power of 2 that is less than or equal to half of memory. So that means we usually can only allocate half of the device memory on the GPU. However, with the unified memory feature, we can essentially oversubscribe the memory by allocating more than what is available on the device memory. This works by putting the extra memory on the host side and use the page fault mechanism when they are accessed. So that means we can further relax the requirement n by increasing the value so that we can allocate more than half of the device memory. And here is a graph showing the performance of the application. We can see that the memory bandwidth is relatively stable when n is below 30. However, as soon as n reaches 31, the performance is immediately brought down. This is because the GPU is issuing many simultaneous page fault requests to the CPU, many of which lies on the host memory. The page fault engine is completely saturated with random paging requests. In addition to that, because almost every single request is completely random, the page fault size doesn't really matter at all in this case. The page fault engine is transferring a lot of useless data in this case. So that means the pressure on the memory system is shifted completely to the page fault engine instead of the memory system. So far, we've been focusing on benchmarks behaviors from per application basis. To further capture the different behaviors across all applications, we used principal component analysis on all benchmarks. The metrics we used fell into 5 major categories in an attempt to capture as many aspects of application behaviors as possible. These categories include the utilization efficiency, the arithmetic unit-related metrics, the stall-related metrics, different types of instruction counts, along with memory and cache statistics. The metrics we used is listed in our paper. Here is a graph showing the first and second principal component space of all applications in Altis. We can see that even with the same application is exposed to different data sizes or different CUDA features, they usually tend to exhibit different behaviors under different settings. This shows data size and CUDA features have direct impact on application behaviors. In the future, we plan to bring more CUDA features to more workloads. Some of these features likely requires changing the programming patterns. We will also introduce more workloads to Altis to keep it relevant to modern GPGPUs. Meanwhile, recent work on HIP and ROCm by AMD makes it possible to bring CUDA code into other platforms. In conclusion, Altis demonstrated the importance of having varying data sizes and CUDA features, as they have direct impact on application performances and behaviors. It is also important for benchmarks to adapt to modern application domains. Thank you for listening to this presentation.